Okay, we're recording to this computer. I hope this recording makes it. Yeah, so I put something on the agenda about Git SSH efficiency. I guess I can open that epic and share my screen. So this is sort of leftover from the work we did last year to make the transport used internally between Workhorse and Gitly more efficient. Okay, step back. So we made this cache to make Git fetches for CI faster. Then we found out that we couldn't get the data off of the Gitly server fast enough because the transport was inefficient. Then we optimized the transport, but only for Git HTTP, because that is the dominant workload on GitLab.com, because CI, our own CI, uses HTTP. But it seems strange to not deal with SSH. And so that was left over, or that was cut from the epic because we needed to keep the scope. Pardon me, we needed to keep the scope down. But I now started working on that. So that is, I'm happy about that, because I think it makes for a more compelling story to say to people, hey, we made Git fetch more efficient, and not, hey, we made Git fetch more efficient if you use HTTP. And I know anecdotally that some large self-managed customers have their own custom CI infrastructure that runs everything through SSH. So for them, it would be really nice to also have this optimized. And also SSH is like, at one point I did a measurement where I saw 1,000 times more HTTP traffic than SSH, but since then I usually see it now at factor 6. So it's still not, it's not nothing on GitLab.com. It's not the majority, but it's not nothing. So yeah, working on that now, and it should be fairly straightforward, although I did run into two rather subtle problems where I thought, I'm glad I run into them because I've worked on the code that has the problems, so it's probably easier for me to fix them than for somebody who doesn't know the code already. I don't mean that to sound like I'm smarter than people, but I just I think it would be annoying to find these subtle problems if you don't already know your way around. So I guess maybe it's a mess I made, and I feel like I can clean up the mess by solving the subtle problems. Oh yeah, I got a flame graph here. That's fun. So this is a flame graph against Omnibus. And if you look at that, so this is doing 20 shallow clones at once. So it's sort of simulating a CI job. The shallow clones are about 100 megabytes.
I wanted to say, Jakob, I looked at this yesterday, and this was just such a beautiful way to illustrate the problem. I just had to tip my hat to you.
Oh, thanks. Yeah, just a big fan of flame graphs. One thing that I found interesting is that I made a point of making sure, if you look at the flame graph for SSH, you see SSHD in there. And it's, actually, I can't find it now, but it has to do encryption. But I can't see the encryption in this profile. But I suspect a lot of this is user space time spent doing encryption. And the funny thing,
we can get symbols for the libraries if you care about that, to
right,
fill in those.
Okay, so those are, I think I'm okay, although it might be interesting to look into that at one point. What I found interesting was that when I set up Nginx, I thought, okay, let's also run Nginx with encryption. And you can see here that it's doing something with AES. I don't know what this is, but this sounds like encryption to me. And it's sending the same amount of data, but it's using way less CPU. So this is 430 samples, and this one is 1100 samples. So almost 3 times more in SSHD. And that has nothing to do with the Git fetch transfer or anything like that. That's just because they are different programs doing the same job. So that was, yeah, I found that surprising. But yeah, if you look at the status quo with GitLab Shell, you see all this time spent in garbage collection. And also over here, you actually twice, it's pretty terrible. And that just goes away.
SSHD point, I was curious, since this was obviously a whole host profile, I'm assuming this is something you captured on your laptop?
No, I did I made a cloud VM, and I did an Omnibus install.
Okay.
So it's still sort
Got
of
it. Okay.
the full GitLab stack in production mode, but it's
Okay,
not doing
great.
anything else except my benchmark.
That was my question. Could it be unrelated background workload? But it sounds like no. That's great. Okay.
No, it shouldn't be, because it's just a VM that I set up. You can see like little things like Prometheus in there and Redis server and whatnot, but nothing. I mean, oh, that's an interesting one. I am running SSHD and I use my perf profile to my perf is extracting the data through SSH, but that happens after the profile is done. I have my perf capture script goes in via SSH. It runs perf record, but that goes to disk. And then it runs perf script, and the output of perf script goes back through the SSH connection. But that happens outside the profile, so that cannot mess up the profile here.
Agreed. Yeah.
Yeah. So I don't think it's that. Yeah, so it's SSH. That was a funny thing to see. But yeah, GitLab shell and Gitly are just using way more CPU here, and it's not even funny how smaller these two are over here. So I think that will be better. Yeah. I think I even have a flame graph for that. Sorry, I'm rambling, but I do have the flame graph. Let's see. Is this it? Yeah, so this is a flame graph without. It's a different workload, but it shows the point. And this is a flame graph with the new code. So GitLab SSHD is actually not what we run in production, but it's what GitLab shell. It's the combination of, it's an integrated combination of GitLab shell and SSHD. So that goes from 1400 to 800, this example. And yeah, it's still spending a lot of time doing encryption. But in the status,
workload's comparable. Is it?
Yeah, it's the same. It's the same workload.
Okay.
It's just, it's doing it's a cache hit of 1.2 gigabytes. So it's 1.2 gig transfer.
Okay.
And yeah, you can still see the encryption workload, but then you also see the garbage collection again. And also in Gitly, you see garbage collection over here. Guess that's the only garbage collection trace. Yeah. But the funny thing is that in this trace, Gitly isn't garbage collecting at all. Or I'm sure it is, but it just doesn't show up in the profiles.
Yeah. It's reusing the buffers. That's great.
Yeah, we still don't know if that is the ultimate explanation of why it's faster, but it's my best guess that it's really the garbage collector. Yeah, so that is ongoing.
Sweet, that's fantastic.
Thanks. So next one is you, Matt.
So I don't know how interesting this is going to be to folks, so I'll just keep it really short and let me know if you want to go into more detail. Okay, stop that. Okay, so screen share. So Gitly. Okay, so Gitly it does not have repeatable builds right now. Repeatable builds are desirable for a few reasons. One of them being when we ship a binary, it's if the builds are repeatable, then it's much more straightforward for security engineers to audit that the binaries that we're shipping are
haven't been tampered with,
actually built
yeah.
from haven't been tampered with and really are built from the source code as we advertise in the way that we advertise. So currently our builds specifically for Gitly are not repeatable for, as far as I can tell, exactly one reason. We set this. Let's see.
We inject the build time.
Exactly. So this build time is defined here in this make variable right here, and make variables can be overridden on the command line. We inject it here when you run a go build. One of the options you can give to the go build invocation is this LD flags option, which takes a single space delimited string as an argument. So this is part of its argument is giving the -X option, whose syntax is saying we're going to override a a Go variable symbol. This is the package path and the name of the variable, and this is its value. So essentially, the Go binary is going to contain this symbol with this value, and we can make our build repeatable by providing any constant string for this value. So it can be a real timestamp, it can be, you know, foobar. In my repeatable build script, I just gave it a dummy value of dummy timestamp placeholder. But this is the syntax for overriding a make variable when make runs, and this is just telling make to run in parallel, and this is the build target, whose name is conveniently build. So what we're going to do here is I'm going to run this script, and it's essentially going to run make a few times. The first time it runs, it's so we're gonna show we're gonna just summarize the status of this repo, and then we're gonna do one build and describe several bits of metadata about it, and then we're gonna have a loop here that does that build repeatedly and show a one-line summary of the SHA-1 hash over all of the binaries that get built to show repeatability. So that's that. So I'll run it. It takes a couple minutes to run, and I'll narrate the results while it's going. So scroll up so it doesn't go off the edge. So this is the first line of output. So we're just noting that we're running on the master branch, and this is the most recent commit. And I've got a local diff. This is not related to the repeatable builds, but I've got a local diff where I removed this one pseudo target from the make file, which was inhibiting make's parallelism. If you run make-j and this target is included in the make file, then the -j gets basically ignored, and every build target gets built serially, which is completely irrelevant for repeatable builds, but it was germane to the task that I wrote this for. So you can ignore that if you please. So this is running the initial build. Because I've already done a build since the make clean, the output is pretty concise. If you do a make clean first, then it's pages and pages of output. So this is kind of a quick output. And this is kind of the summary. So for each of the 10 or so binaries that we build in this daily build, I'm going to output the Go build ID and the GNU build ID, which this is what it looks like when there isn't a GNU build ID and we ask to show it. There's a separate branch that does provide these, just for context, and everyone on this call knows about this already. And then this is just a SHA-1 checksum over the binary contents of the byte contents of each of these binaries. And then this is a hash over this output. So it's effectively capturing whether or not any of these binaries is changed. And so we're going to compare this value to the output when we do these runs repeatedly. And so I'm scrolling down a little bit so we can see the 3 loops that we ran. And we've got, as you can see, we've got the same value each time. And thus the build is repeatable. Yeah, so that's pretty concise.
That's
so
awesome.
This is So this is I think this is compelling evidence that that build timestamp is the only uncontrolled source of variation that's preventing our builds from being repeatable, which is fantastic.
Where do we know that?
That's a great question. I didn't do this research, so I'm repeating what I heard from another thread back in December. It sounds like the only way that we use the value the value that gets statically bound into the binaries is to support one of our Prometheus metrics that wants to have a trend line showing the build timestamp.
Yeah, but so I wonder if we could just take the one of the timestamps from the commit we're building.
Yes. So we could certainly do that, and we could. I think that would be very reasonable. So I think. So I'm gonna read. You don't need to see the screen share anymore. Sorry. So this is from back in December, so I don't know if anything has changed since then. But the last time we talked, the last time I was involved in the conversation about this, Stan had made an MR and then closed that MR without merging it to do exactly that. I forget if it was either removing the build timestamp or setting it based on the most recent
in a deterministic way.
Exactly. And the reason we had to close that is because the fact that the builds are not repeatable, which this is the only thing making sure that the builds are not repeatable, means that every time this is a chain of side effects, really, and we need to deal with the chain of side effects so that we can make the builds.
What is the side effect?
The side effect is this is what's making every time we install a GitLab EE package on the GitLab host, the reason that we're able to trigger the restart behavior for the MR that you made for Omnibus recently is because of these build timestamps being guaranteed different for every single build. If we make them non-repeatable, then if we do, we deploy once or twice a day at this point. So so then we go back
to that the proc self XC is it has deleted in the name because the inode no longer exists, and then
exactly it undoes the benefit that you just added in December to get these consistent restarts. It partially undoes it.
Yeah, well,
and as far as I know, that's the main drawback. Like, I mean, the really the kind of the ideal situation, I think it would be to have the package installer restart Gitly
this sounds like something we can cheat around, because there must be some ID that is changing for higher up the chain, and we can just say restart this if the omnibus version changed or something, and then it doesn't matter.
I think so. I completely agree, and I think that's the right path forward. We just have to, we essentially just have to do that work, and then we can make the build repeatable. And that's what I wanted to show.
Okay.
Yeah.
Right. Yeah, because it's not enough that we install the exact same binary, because perf will still think the file you want no longer exists.
Yeah, exactly. Because the deb package manager will still unlink the old inode, even though it's replacing it with a different inode with exactly the same.
Why would it check that? Yeah.
Exactly. Yeah.
Yeah. Okay. Well, that sounds fixable, and it also sounds like it's fixable. Like it's reasonable on its own. I mean, think so. I mean, restarting based on the hash is also fine, but what we really care about is whether the package gets reinstalled. So if we know the ID if the package has a unique ID that's changing, that is a better signal for restart than the hash of the binary.
Yes, true.
Yeah.
Cool. Okay. So that's that topic. Any unless folks wanted to talk more about it, I'll move on to the other bit. Okay. Cool. So this is about stripping ELF binaries. So I don't have anything ready to screen share yet. I'll just keep using this one. Go binary is kind of bad. Oh wait, I do have something. We'll do this. Yes, this will work great. Okay, sorry, I'm winging this. So this is a copy of our Redis server binary built and distributed by our GitLab EE package. And if you run file on it, you can see that it's beautifully both not stripped and claims to include debug info.
Can you explain for a moment what that means?
Yes, absolutely.
What those two things mean.
Absolutely. So stripped means, so there are a couple of options. That's exactly what we're going to walk through. So,
I know the words, but I don't actually know what they mean.
So the easiest way to talk about it is with some context. So I'm going to just narrate the output here. So this is a generic. So what we're going to talk about here is generalized to essentially any ELF binary. So you can apply the same logic to.
ELF is a container format for executables.
Yes, ELF is executable Linux format, I think is what it stands for, something like that.
And
yes,
so it arranges the different pieces that make up an executable, and it has a table of contents and headers and whatnot.
Yes, exactly. Yeah. So we can go into as much detail as is interesting. I usually use bin ls as kind of an example. So you can see that it also is an ELF binary, and we can.
This one is stripped, whatever that means.
Correct. Yes. So, and it's got a bunch of other sections. So we'll use this to, as a contrast.
Are those
point. So
numbers
first,
are those numbers sequential in the left column?
yes, they are.
Okay, so this one is 29, and the other one is 40. So there's fewer things in it.
Yes, exactly. So, so I'm going to focus on the one that's not stripped and does have debug info first. So the with debug info piece is the easiest one to talk about. It's these sections that are named .debug something or other. So there are there's a kind of a bit of a historical pun that ELF is the format for the binary, and then someone thought it would be cute to call the debug infos dwarf.
Yeah.
Yes. So it's traditional but not mandatory to have the dwarf debugging infos embedded in ELF binaries, and they don't have to be, but they can be, and it's typical to make them so.
And just sorry to better understand what we're looking at. This this table has a column called off, so I assume that's offset, and it appears to be sorted by offset. So we can think of this as a map of different sections of the file.
That's exactly right. So so
we can literally say that one thing comes after the other, because it's like the bytes of inter-P come first, and there's one C of them, and then the next one, the rest comes after that. That's what we're looking at here.
That's exactly right. So this is the offset within the file, and this is the size of that offset in bytes. This column, this is the virtual address, and one of the significant. So this is a great time to talk about this. So so offset within. Okay. So
these don't get mapped into memory.
That's exactly right. So so when you run a process. Different pieces of the binary will be mapped into statically defined addresses.
Because the process has its own
addresses.
The process has its own address space. Correct. And it's Linux's job or something's job to read this and put chunks of this file in the address space where the program expects it.
Yes, exactly. So that's exactly right. So so in any running process, we're going to have essentially exactly the same mappings into the virtual address space of that process for this binary. They'll of course occupy different physical pages of memory, but from the perspective of the process, it's virtual address space.
We never see that. Like the process only sees the virtual address space. Yeah.
Yes, exactly. And so one of the interesting takeaways here is that some of the sections don't need to be mapped into memory. So they exist in the file, but they don't actually get mapped into the address space.
And the convention is that so address 0 means that the thing that maps them into memory skips them.
Exactly right. For any ELF binary, there's kind of two views on the same chunk. So I'm going to gloss over the difference between section headers and program headers, but except to say that program headers are really a collection of one or more sections, and some sections like these debug infos don't actually get included in program headers because they're not required for the program to run. This section-oriented view of the binary shows us the entire binary, including things that don't actually get mapped into virtual memory, which is why we're able to see these things.
Yeah.
Okay. So that's kind of a roundabout description for what this with debug info refers to. It's essentially, do we or do we not have sections that are named .debug something or conversely .zdebug? Because
and what these are for is that if you use GDB to attach to the process, they help GDB, or what is this stuff for?
Yes. So so when so there are a bunch of different levels of debug that we can set. -G. I'm trying to get to the right section that talks about it. Yeah, sorry, I thought this would be an easy way.
No, the line at the top says it. Produce debugging information. GDB can work with this debugging information.
Yes, exactly.
Yeah.
So so there are various levels that you can request. So so let's go back up to this one. So the the debug infos can cover something as can cover a variety of different types of data, including things like the complete function signatures, so that you know what the arguments are to a given function. Potentially as detailed as the source code line numbers associated with individual assembly instructions.
Yeah.
Which is where you get sections like this.
Yeah.
So they. Go ahead.
And they look quite big if I look at the size, because some of them are 6 digits in hex.
Yes.
So that will be hundreds of kilobytes, or not if not a megabyte.
Yes, exactly. So I'm going to switch back to just looking in this directory. This is the original binary, and these files are, which you can see are except for this first one, are copies of the binary with various levels of stripping or compressing applied. So we're going to essentially repeat this operation.
So can you run lslh so that we get the helpful? Yeah. So it goes from 12 megs to 2 megs. Yeah. Wow.
Yep.
10
exactly.
10 megs of debug stuff.
Exactly. And the Reddit server binary is not a big binary, so this is a huge percentage difference. It's like a 5x difference. So we've talked about the scroll up again. We'll just look at it again here. So we've talked about this. Let me answer the question about stripped versus not stripped now. In fact, why don't we do this? So we'll run the file on all of these files, and you can see that I'll explain what we did to generate each of these files in just a moment. But you can see that only the last one is considered stripped. So I know I haven't shown this yet, but this one is removing all of the debug infos. And you can see that we no longer claim to have debug infos, but we're still not stripped. And this is the minimum thing that provides useful information for building flame graphs. So going from 12 megabytes to 2.1 megabytes is perfectly acceptable in terms of still having useful.
It's still useful enough. Yeah. Yeah, because
Exactly.
we really only need to know the names of functions, the names and addresses of functions, but nothing else.
If we're gonna do like binary analysis or digging into like if we wanted to instrument calls to a function based on the second argument to the function having this particular, a value.
Yeah, then you need to know more, and then
it's super helpful to know more. Exactly, you can get by without it, but it's so obnoxious that you wouldn't.
Yeah.
So yeah, that the debug infos provides wonderful support for GDB, but we don't. But even outside of GDB, they can still be useful for custom instrumentation. But generally the symbols are.
But it costs a lot of disk space, so it's something we. So what is so you're saying the Omnibus default is to include all these symbols, all this debug stuff?
Yes.
Okay. So I think
I'm
Marin
not advocating getting rid of.
Oh, okay. I remember Marin not liking the Omnibus packages always getting bigger.
Yes,
I think nobody likes it, but Marin used to head that team. It was team lead of the distribution team for a long time, so I think he
got it. Okay, that
he
makes
would be
sense.
interested now. Yeah.
Well, let me mention this. At least for the Debian packages and possibly for other packages as well. I can't remember what the multiplier was, but it was at least like 2 or 3x smaller.
Do not have
by switching.
The debug. Yeah.
Actually, no. Even keeping the debug infos without changing, without doing any additional stripping, the package is basically not very efficiently compressed. And I don't know Omnibus well enough to know how to set this flag, but when I build the package, when I build a package with Debian tools locally, I can produce effectively. I can extract the contents of the package of the Omnibus GitLab EE package and repackage it and get the package much smaller by altering the compression level. And that I think is our quickest path to get the package smaller.
Well,
and,
if you can,
actually, Jakob, you'd probably be a great person to pair with on
yeah, if you can turn off the screen share for a moment, I can show you where this happens.
Yeah, great.
So Omnibus has 2 main parts. There's the part that does the build, and then there's all the chef code that runs after you've installed. That is GitLab control reconfigure. All
Okay.
the build stuff is in config,
Okay.
and config software has the build definitions for all the components. So somewhere in here is Redis,
Yes.
and
What about the
we-
higher level, building of the package that contains all of these components? Where would I find that?
that is encapsulated into the Omnibus gem. So that is harder to get to, but what you
Yes. Okay.
the basic structure is that you have a build route where you run basically make somewhere, and then you run make install,
Yep.
and you can set C flags beforehand. You can apply patches. So if you look around in the config software directory, will find various examples of how to tweak these builds. But this is, I don't know Debian builds well, but I imagine this is roughly also this is just what you need for a package build. And the actual step where you copy these files, actually I think make install copies them into, on Omnibus machine you already have opt GitLab, so make install copies the files from the build route into opt GitLab, and at the end of the build, all of opt GitLab gets bundled up into either an RPM or a deb.
Exactly, and that last step is the one that I need to modify. Although
So
this is
why do
also
you need to
useful
be
for
there
other
at the end?
purposes. Because this is a package level compression that needs to be turned on. I focused on Debian packages because that's what we work with on GitLab.com. But I suspect that RPMs, for example, as another packaging framework, have a similar option. Essentially, this is switching to XZ compression, and newer versions of the Debian packaging framework default using this, but the version that Omnibus uses doesn't default to it, but it's still supported. So we just need to effectively set an option to tell it to use XZ compression. This is going to make it doesn't make the extracted contents of the package any smaller, but it makes the package itself much smaller.
Yeah. Yeah, I'm not sure that sort of crosses over into the Omnibus gem.
Okay.
And I think we actually have a fork of that, but so this somewhere, it's been a long time since I've been in here, so I don't know what happens where, but this thing,
yes,
that's
okay.
not it. Packagers, deb.
Yes, this will be.
Yeah, it writes the control file, does the stuff. Create
Yes.
deb file. Oh,
that'll be it.
I'm so not used to these jump to definition things, but
yeah.
Fake root, dpkg, deb, compression params. So if
yes,
compression strategy, okay, where does that come from? Invalid compression strategy must be one of the, so I think they only like these. Is this one of the, does any of these sound right?
It's been months since I looked at this, so I'll need to check back on my notes, but I think no, it's let me see if I can find it quickly.
So that is a new option. It says here that it's got added later. So it sounds to me, looking at this, that this is going to deny list XC. So there is a mechanism. So in this file, we should be able to somewhere say that we want to use a compression mechanism, probably in this block. But if we would say XZ, then I think this thing is going to reject it.
Okay.
But then there's still one workaround, which is that we have I think we have a fork of Omnibus because we had to, because of reasons. I don't remember what they were. GitLab.
I think I remember that too. I mean, I remember seeing a mention of that. I had nothing to do with doing it.
So why isn't this loading? I don't know. So we do, okay, this is 5 years old. We're probably not using this. No, wait, 6 months ago, 1 month ago. So we
Yeah,
do
okay.
use this. So then if we go in here
Mm-hmm.
to the packagers, to deb, and then there's the word extreme.
Yes.
Oh, for XE. Oh,
Yes.
extreme means XE.
Uh-huh. Okay. Perfect.
Okay, well
Perfect.
then it is supported. So then
That's
my guess would
lovely.
be that if you go into this, sorry, forget about this.
Mm-hmm.
You go into this file, so that is
Mm-hmm.
config projects GitLab, and you look
Mm-hmm.
for the deb section.
Mm-hmm. Mm-hmm.
If you're lucky, you can now set compression strategy extreme.
Okay, fantastic. Awesome. Thank you. That's great.
Well, maybe that was also what we're supposed to do here, but I just thought.
No, that's fantastic. Okay, so I'll screen share again, and we can wrap up the bit about symbols. So, okay, did I get that right? Yeah. So, symbols. Okay, so broadly, so there's a few ways to kind of talk about different types of symbols, but in this context, I want to differentiate between dynamic symbols, which are defined here, and those get resolved by the runtime linker, versus symbols that were already resolved by the static linking that happens during the build, and those are defined in this symbol table. And this is the string table that gives us the names for those symbols.
Right. So symbols, just for my understanding, to see if that I got it right, are the names of functions, because the
variables
because the CPU doesn't care about variable names. It just uses addresses in memory. But if you want to make a pretty flame graph, you want to know that this address is actually, it has this human readable name, and those names are the symbols.
Exactly. That's exactly it. And so the difference between, and I wanted to show this empirically. So this one is stripped of symbols, and this one is not. And so we can do delf sections for this one. Diff that with thing for this one. Oops, this one that is completely stripped. We can see the only difference is that we've ditched the symbol table and the string table that goes along with it, and just this is also a string table. This is the section headers string table, which incidentally is what we're using to get the names of the sections.
And so it's now 16 bytes shorter and moved.
Exactly. So that's it. This is what stripping symbols means. It means getting rid of these two sections.
And I guess maybe I was so confused about the symbols, because there's actually, maybe it's not about the human readable names, or the string tab are the human readable names, but the symbols are also about finding functions that are in linked in at runtime. The dynamically linked.
That's exactly right. Yes. So that's the dynamic symbols. So if we do, there's a few ways to inspect symbols. NM is the shortest one to type. So that's what I usually default to. So if we do NM on Redis server, which is not stripped, let's show this again. So this one is not stripped. So if we do NM on Redis server, we get a bunch of symbols. And if we do Redis, and if we do the same thing on the completely stripped one, we get nothing. And NM specifically says it has no symbols, no normal symbols, but we can still do, we can still find the other 3,000 dynamic symbols. That's right. Those are that'll be consistent for all of our Redis server. Copies of this binary, because stripping does not and cannot remove these, because these have to be resolved at runtime.
Oh, and yeah, they also have a string tab, so they're
yes.
Is that so you can? So you can print good error messages, because I don't see how the
not only so the so a lot of these symbols are okay. So there's two reasons to have dynamic symbols. One of them is if the symbol is part of Redis server but gets exported, in essence, to make it available for other libraries that might want to call it, for example. The build framework is very similar for shared libraries versus executable binaries. And just for context, and the other reason is, I'm going to try to find some examples.
Oh wait, but no, I see why the names have to be there, because what else are you going to identify the things in the libraries by?
Yes,
Yeah,
exactly.
that's what so the strings are keys into the library.
Yes. So we can also look at the spelling is slightly different for different tools. Yes, so this is the dynamic linker is responsible for resolving what's called relocations. And part of the contents of the binary is to effectively say, here's how to find this symbol that has to be resolved by the runtime linker. So for example, glibc is expected to provide the right function, and this is the type identifier for the kind of relocation that we're talking about. So it's
a slow jump, whatever that means.
I think this is shared library object, if I remember.
Oh,
I can't remember.
okay. I thought it was I meant slow, the missing W, but yeah.
Oh yeah, right.
No, this is
so
shared library object also sounds good.
Yeah. So that's so this is how we access show the top of this list. Yes, there are other types of relocations, like user relocations that are at relative offsets within the binary. And they don't have pretty names, but the ones that this is to your point, the ones that have to look in libraries that are outside of this binary, that have to be brought in by the dynamic linker on demand, those will always have names and some string that identifies which of the shared libraries is expected.
Yeah, what library we're going to. Yeah.
Exactly. So that's kind of a quick tour of stripping. And oh, I didn't actually do any stripping. Let me show you.
I don't want to be rude, but everybody else has already dropped off, and
right, yes,
we've been going at it for an hour, so.
Oh yes, okay. Well, we can stop here then.
Yeah, I was going to ask, like, is this a good time to stop, or do you want to still show something? Yeah, okay.
Yeah, no, totally a good time to stop.
Yeah, then let me see if I can stop the recording without